Hey, it's 10:35. Okay, everybody hear me? Nod, nod. Put a strobe on the screen. We're going to take a look at that. I'm going to explain it. We're going to go through some basic terminology. We're going to talk about some things that some people are familiar with, others aren't. I'm sitting in our classroom, so in 3 weeks, hopefully you guys will be in here as well, and we'll get to do a little bit more interaction. This class is so much more fun when you interact. I've got a dry humor that I play off of students. So if y'all get really quiet, I'll either demand you talk or I'll just get really boring because I feed off of your reactions. That being said, let's see, there's already something in chat. What is it telling me? Can you please change my name? Okay, all right, looks like they fixed their issue, so okay. All right, nobody's waiting to get in, it looks like. So let me share screen. Let's see if I can find it. Maybe it helps if I open it first. So let me just open this strobe and then here we go. And there we go. All right, so what I've shared on my screen is that you can see that there are 4 lines, A, B, C, D. It says, in each case, the sphere is moving from the left to the right. Okay, so if we look across A, we see 1, 2, 3, 4, 5, 6, what looks like 6 balls across the line. It's really just one. And using flash photography, every second or every 2 seconds, every second, it took a picture of where the ball's located at. So in line A, after 1 second, it took a picture and the ball was at position 0. At 2 seconds, it took a picture and the ball had moved 2 meters because it's sitting over position 2. Okay, we can see that after 1, 2, 3, 4, 5, after 5 seconds, it was at position 8 meters along. If we get the idea, so that was trial run A, and then B is a different ball, C is a different one, D is an even different one. Okay. So I'm going to leave that up where you can see it, but now we're going to see it says we want to rank the magnitude of displacement over the first 2 seconds. So we don't care about the 4th, 5th, or 6th time that we took a picture of the ball. We only care about the first 2. So take a look at it, get an idea of what you want to answer, and then we're going to walk through it. So I'll give you like 30 seconds, and then we'll talk through it. All right, that felt like an eternity, so we'll say that was 30 seconds. So we want to know that rank the magnitude of greatest displacement over the first 2 seconds. So which one went the furthest in the first 2 seconds? This is where you got to talk.
B.
All right, B like boy or D like dog?
I said D. Boy.
Okay, so I got a boy, I got a D, I got mixtures. So let's talk through them. Do we want to start at the top or the bottom? Do you want to start at A and work your way down, or D and work your way up? Talk.
It doesn't matter.
Oh, you got to, all right, whoever just said it doesn't matter, you got to pick. Where am I starting? The top or the bottom?
Top.
Start at D and work up?
Sure.
Okay, that's probably not what you said, the way you said sure, but okay. All right, so at 1 second, D is at 1 meter. At 2 seconds, D is at 6 meters. Okay, so in 2 seconds, D went 6 meters. 6. All right, I got enough fingers to count that one out. C started at 0, and at 1 second it was at 0, and at 2 seconds it was at 3. All right, B started at 0, and at 2 seconds it was at 0.4 meters. And then finally, A at 2 seconds was at 2. So if we were to look at the most displaced, the greatest displaced in the first 2 seconds, D delta, the bottom one, definitely went the furthest at 6. C came in second at 3, A came in third at 2, and B like boy came in last because it started out real slow moving there to only go this far in the first 2 seconds. All right, so I'm going to take that away. Does that sort of make sense as far as what we were looking at? Now, when we're first looking at it, it may be confusing because you may not be used to these warm-ups or these strobes or these type of things, but don't worry, as you kind of go along, you'll start to get the hang of them. So no worries there. That just kind of gets us started in physics. You know, this is AP Physics. We are going to hit the ground running. The point of this class, the whole purpose of me being here and trying to help you guys first is to teach you physics. How do I measure that? Your scores on the AP1 exams. Your goal on day one should be that you're going to take the AP1 test. If it's not your goal, I would question what your goal in being here is. Most people feel overwhelmed the first few weeks in this course. That's normal, so embrace it. I would say by the 6-week or 9-week mark, you're going to know if this is where you should be and where you should continue. Last year, out of 2 classes, I only lost 2 students to dropping. So it's, I would say that for the most part, people acclimate. It feels like you're drowning at first, but you'll acclimate as long as you're putting the work in. You guys are all face-to-face, so your IHS students, you should know that your school has the highest scores. We average higher than the state, but of course the state, we're talking about the whole state. We also average higher across the district. My classes in particular, we had the highest average of passing. So passing is a 3, 4, or 5. So as long as you're putting the work in, you're in an environment and you're within a good group of students that you can help each other get to start with passing, and let's push everybody to a 4 or 5 on this test. Now, how are we going to do this? It's going to be a lot of work, and let's start out by taking a look at Canvas. So let me flip this over where Canvas is going to be visible, and let's take a look at things. So if I share this screen, if you were on campus last year, you saw this a lot going into the spring. Of course, the spring was a bit more relaxed than what we're going to be here in the fall. We're going to treat this like a real school year and not just coasting to the finish like we did in the spring. But when you come in, you're going to find your course that says AP Physics 1. It has my name there. I don't know if it has your name there or mine when you go in, but when you go into the course, no worries, this is what you'll see. There are navigation on the left. You can see a lot of them are hidden because they're really useless for you. If you just concentrate in the center, that's really where you want to be. It has teacher information, tutorial times, syllabus calendar, general information. This button just kind of puts you all into there. So if I just click here, at the very top, you can see AP1 syllabus. This is really just for board reading because for the most part, it's just one of those necessities. A little bit more important, the 9 weeks calendar will show up there. If I click on the calendar, we keep this pretty up to date. It's pretty accurate. While we're in the first 3 weeks of school, the synchronous means this is what we're going to do together on Zoom. Asynchronous means that this is what you should be able to do that day, probably still during class time. And then homework is stuff that you're going to work between classes. Now, I know this is day 1 and there's a lot of things on that list, but that's okay. We're going to work through them pretty quickly. The homework is long in list, but it's not long in due. And that same homework is repeated the next 2 AB cycles. So really, we want you to finish that this homework by September 24th when we'll have our first assessment. So you can probably do it all in an hour. You have a week and a half, plenty of time. All right, so if I back out of the calendar and I just go back to here, if we scroll through here, we can see that Mr. Hennessy is one of the 3 teachers that teach AP1, blah, 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 blah. No one cares about him. There's your teacher, such a handsome fella. This is my tutorial times, though I can set up something individually with you as necessary. Morning tutorials, if you haven't heard, when you arrive into class or you arrive to school every morning, you have to go straight to first period. Doesn't matter what time you get here, 8 o'clock, 8:15. So morning tutorials will all be through Zoom. So you'll basically go to your first period, you'll put on your headset, you'll Zoom some other teacher, whatever teacher you need help with, as long as they have tutorials set up. Afternoon tutorials will be your only time to have face-to-face tutorials. So according to my schedule, I have afternoons on Mondays, Tuesdays and Thursdays I have mornings. This is Miss Doyle. She's the 3rd teacher that teaches AP Physics, and then her tutorial schedule as well. So that's what you kind of get on that front page. If I back up to when you go into the coursework, a little bit more important. This is where you're going to find everything that we're doing as we're going along. These Zoom meetings that we're having for classes between let's see, 3, 6, 7, 8, 9, 10. I think there's 10 sections of the class. Across those 10 sections, we'll record one of them and post, well, they're all recorded, but we'll post one of them to Canvas. So if you're absent, you're sick, or you had to clean up your sister's room during class, well, you can still get to class information. Unit 1, we go into there, and there's a cute little description, and it shows us week 1 with the dates. Today's the 13th, so if we go into there, it brings us into today. It has essential questions, objectives. Nobody really reads those, but what's most important is Thursday, Friday. So today's the A-Day Thursday. We've got introductions. That's what we're doing now with Canvas and the calendar. We did the strobe displacement because I don't care about the order that's here. I like to do my own thing. We're going to do a discussion. It says quick is relative. We'll do another probe, then I'm going to turn the day over for you to do the walking lab, and then you've got the homework. You've got links to all of these. I'm going to ask that the walking lab be submitted back to me by end of the day. We do attendance during the first 3 weeks at least. Rules will change, but you either have to be in the Zoom or do the asynchronous activity to get credit for your classes during this time. So this being AP1, I kind of expect both. I expect you to be here as much as possible. I understand when you can't be, that's things happen, but don't use the asynchronous activity as being your get out of lecture free card, because you're gonna miss a lot. We move fast. Okay, so that's my very quick discussion on all of that. I'm gonna stop sharing my screen. So we should all be somewhat familiar with Canvas. I've just shown you a little bit of our course. And if you have questions, concerns, problems, I have an email address and you can contact me most anytime. I get them on my phone and I respond most of the time, as long as all is cool. So let's get into physics. We're, what, 13 minutes into class and I haven't talked about physics much, so let's do that now. All right, I'm gonna start with fist to 5. So fist means no, 5 means yes. Okay, so scalar and vector. Who has heard the term scalar and vector? I'm not gonna pick on you, but no, yes. No, 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 no. Okay, all right, so it looks like a bunch of no's and no there as well. All right, so that means everybody's interested in this lecture because no one's ever heard of it. But as I'm talking, don't worry about writing anything down. I'll tell you when you need to write something down. If you see me write it down, or if I tell you write it down, then write something down. The rest of it, let's have a conversation, okay? I'm gonna read a proper definition for you, but then I'm gonna give you a real life example, then you're gonna be like, oh, that's easy. So let's go there. So scalar is a quantity that is only defined by a magnitude. Now in my on-level classes, if I put magnitude on a test, I get 3 hands in the air and they're like, what's a magnitude? Magnitude's a number. If someone says, hey, pour some milk into a measuring cup, you're gonna say, how much? Half a cup, 2/3, 2 cups, 1.5 cup? I mean, how much do you need for your cake batter or whatever? Magnitude is how much. If I say, how old are you? And you say 16, the magnitude of your age is 16, right? If someone says, how much money you got? The $30 in your wallet, that's the magnitude of the money. So magnitude just means number. How much, how big, or how little, you know, whatever. Now, I like to use cars as a reference because a lot of you are becoming driving age and you're at least interested in being in a car, have been in a car, drove a car, or saw a car on TV. So all of that should be true for everybody, right? So when you're driving a car, imagine you're driving a car, if you don't already. When you're driving down the road, you look down and you always check your speed, right? Because you want to make sure you're not speeding or going too slow and causing a wreck. Now your speedometer tells you how fast you're going. Doesn't tell you which direction you're going, right? It only gives you a quantity, a numerical quantity. So it's scalar. The odometer in a car, you know, the thing that rotates and tells you how many miles you've gone, it only tells you how far you've gone, distance. Doesn't tell you what direction you went. Scalar. Scalar is a quantity that is only defined by a number and not a direction, okay? If we were all go camping, let's say that the campsite is the classroom, because I'm in our classroom right now, and you guys have all left the campsite and headed home, except for Jack. And I'm picking on Jack because he's in a car, hopefully not driving, but he's listening to us. Now, Jack got lost. Jack said, I know I've gone 10 miles. So the other 15 of us are like, okay, I need you to go that way, you to go this way, you to go this way. And when we've gone the right distance, one of us should find Jack, right? But what if Jack told us, I went 5 miles north? Wouldn't it be easier to find him? So that's what a vector is. A vector has the numerical value, but it has a direction as well. So if I gave you a very fancy definition, vector is a mathematical quantity that is represented by an arrow with both direction and magnitude. Okay, so if I were to give you something to remember that by, let me set this up. Let's take a look at that. All right, make sure you can hear. Let's see, share computer sound. And we've got this, share. All right, everybody loves a cartoon.
Hey. I'm applying for a new villain loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Vector! 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 That's me, because I'm committing crimes with both direction and magnitude. With both direction and magnitude. With both direction and magnitude. With both direction and magnitude.
Are we getting the point? No, not yet.
Oh, with both direction and Vector! That's me. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh, yeah!
All right, Vector has both what?
Direction and magnitude.
Direction and magnitude, right? See? Now, when I said earlier, do we know the difference between a vector and a scalar? Fist of 5, show me what you got. That's a lot more 5s than we saw before. Come on, everybody's got a, there we go. Get a little bit more interaction. So we've got that. Now, when we talk about a car, we said an odometer tells us distance. So what would be the vector quantity instead of distance? We would say displacement. Okay, so displacement is a straight line distance from initial to final. Don't write that down yet. You'll have plenty of time to write that down. Speed tells us how fast we're going, but not what direction. So we'll use velocity. When we say velocity, it's speed with a direction. When we say displacement, we're saying it's telling us how far we've gone in what direction, sort of. So let me actually write something. So I'm going to switch screens, but that's all right. You'll just have to watch my terrible handwriting. And let me see if I can do that here. So I share an application and we go to there, share, and I go to there. Oh, might have crashed it. It's gonna make me sad if I crash this. It's not sharing anything, is it? No, okay. See my Chromebook? It's terrible. Oh, here it comes. Oh, no. Did it kick me out? No, the meeting's still there. All right, so give me just a second. Let me see if I can get this to. All right, share application. Share. There we go. All right, Yahtzee, got it. All right, now if we've got this, so if we were to draw something, this is something you can put in your notes unless it's just like painfully obvious to you. If I were to draw something and say, okay, let's call this our starting line right there. So this is that's 0.0, okay? And then this line can be, let's call that, let's see what I put in my notes, 2 miles. So right here is 2 miles. And then way down here, this will be 3, those are supposed to be like arrows, equal sign arrow things, 3 miles. All right, if I start here and I go all the way down there and I come back to here, how far did I go? You got to use words. I can't see you right now.
6 miles.
Well, I went 2 plus 3 plus 2 more.
Oh, wait, sorry. I was thinking.
Oh, wait, hang on a second. Well, that's 5, 6, 7, 8. So this should be 8, right? Because if I went 2, this is 2, and then this is 3. So that's 5 to here plus 3 more. So that should be 8 miles total distance, right? Now, total distance, like if I'm driving in a car, I've gone 8 miles because I went 2 plus 3, and then I went that 3 again when I came back. So my odometers would say 8 miles. But what about displacement? Displacement is different in the fact that it's the difference between where I start and where I finish. I started at 0. I finished at the 2 mile mark. So what's my displacement?
2 miles.
2 miles. Now displacement, so my displacement would equal 2 miles, and I might want to add in east because that's a direction. Where my distance equaled 8 miles. Didn't matter what direction. Okay. Let me give you a different example. I don't know if anybody here has run track, knows someone that runs track, or they themselves have seen a track on TV. Now, I did major in art in college, can't you tell? That is a perfect drawing of a track. I'm just kidding. I hated art because I was terrible at it. But the distance around a track, I've been told, is 400 meters, okay? And let's call this the starting point. So if you run around the track one time, how far, what's your distance?
400.
Around 3 times is 1,200 meters. I can multiply 2. Now, if you've got a friend and they start right here and they go around once, twice, 3 times, and they stop right there, what is their displacement?
0.
To the end of their run, and they're going to be out of breath, and you're going to have to say, you didn't get anywhere. You've got no displacement. Okay, so let's talk a little bit about that then. Oh wait, I'm sharing over here, so I got to stop it over here. Okay, so anybody seen Ferris Bueller's Day Off before? Okay, like 2 people, the rest of you are like, I've never heard of what you're talking about. Okay, shows up on TBS every once in a while. Matthew Broderick from, like, he's older than me, but he was in high school in the movie. He has a friend named Cameron. They both decide to skip school. I think Cameron's sick, and Ferris just skipped school. And he goes over to Cameron's house, and Cameron's dad has a very nice car, the kind of car that's in a showroom in the nicest part of the house kind of car. All right. Put the movie aside, and let's just imagine in real life. Now, I've known you guys for like 25 minutes now, so I know none of you would ever do this, but you probably have a friend that's a little bit mischievous. And you've had 5 months away from school, and maybe you went to your friend's house, and maybe that friend is old enough to drive, and their dad just got, let's say, a brand new Jeep, big tires, the LED lights at night, you know, the whole ground effects thing, sound, got bass, whatever you want, it's there. But the dad does not let your friend drive the Jeep. She's not allowed to drive it. He barely even drives it unless he's going to get the oil changed or it washed, right? But dad's out of town, and your friend's like, let's go to Starbucks. He'll never know. We'll take the Jeep. It's got gas in it. Now, you guys are so conscientious. You decide to stay home, but you're like, but get me a tall chai tea latte. Get me one of those, but I don't want to get in the Jeep because I don't want to get in trouble because I really want to go to the lake this weekend. All right, so we have the whole setup. Friend goes, takes the Jeep, comes back, has your Starbucks. Do they park the Jeep back in the garage, or do they leave it on the street? You got to talk to me. When they were they supposed to be driving? Have any displacement if they put it back where it started?
No.
Want a no displacement so they don't get in trouble? They're going to want to put it back exactly the way they found it. So that way they don't get in trouble. Because displacement is final minus initial. If it started in the garage and ends in the garage, no displacement, nobody's the wiser. Nobody gets in trouble. Don't take your parents' cars out, please, and say it's a physics experiment, because it's not. I didn't assign it. But that's the idea, okay? So in the movie, they take this I think it's a Ferrari out, drive it all around town, then they park it back in the garage and they try to roll the miles backwards, and then it goes shooting out of the back and tumbles down a ravine. It's really a bad issue, that situation. So anyway, I digress. That tells us we know a little bit about displacement. We know a little bit about distance, right? Distance and displacement are only equal to each other if you move in a straight line. If I go 2 miles straight, I've moved 2 miles. My displacement is 2 miles, my distance is 2 miles. As soon as I curve, change direction, my displacement will then be different. Okay, you can draw it out and prove it, but well, what's the point? So we've talked about distance, we talked about displacement, we talked about scalar, we talked about vector. Both of them have a magnitude. All of these have a magnitude, but the vector quantities, displacement and velocity, have a direction. Now the direction can be left, right, up, down, east, west, north, south, but also it can be positive or negative, okay? In your math classes, positive and negative just means on which side of the zero. Most of the time in physics, positive and negative just is directional. I can say that I'm at the origin. If I move this way, that's positive. If I move this way, it's negative. It's just based on moving away from an origin. We can say up is positive and down is negative. As long as we've defined those directions, we can use those as a way to reference. So when we say something is -3 meters per second, it's not less than 0. It's just moving in the negative direction. Does that make sense? If you ever played Mario Brothers, did you ever play the old school Mario Brothers? You know how you could only move to the right in Mario Brothers? To progress in the game, you move to the right? It's like the old school video games. So those left, you couldn't, as soon as you moved far enough right, you couldn't move back to the left because to the right was always positive. So generically speaking, we'll say right is positive, up is positive, left is negative, down is negative. It doesn't have to be that way, but we'll just kind of consciously make that agreement that when we say positive, we mean to the right, negative to the left. It makes things simpler. Let's see, we talked about that. We talked about that. What else we got going today? All right, so I said that you only need to write down things if I write them down or if I tell you, hey, this is important. I'm going to give you 3 physics facts. Today, they're going to be definitions. They sort of make sense. They're a little formal. But when we get into FRQs, the free response questions, we have these for most quizzes and all tests. These get you ready for the AP1 exam. And for any FRQ, you should start with a physics fact. Like you read a question and you're like, well, this is a fact and this is how it relates to the question. You'll get a better score that way. So I'm going to give you a physics fact and I'm going to give you a few minutes to write those down. So let's see, right there, share this. Okay, so these are your physics facts. They are kinematic definitions. Displacement indicates how far an object ends up from its initial position, regardless of its total distance traveled. Average velocity is the displacement divided by the time interval over which the displacement occurred. Compared to instantaneous velocity is how fast an object is moving at a specific moment in time. Think about a long trip where you're passing cars, you're driving faster, then you have to slow down because there's a wreck on I-20, then you speed back up. You can average out and have an average velocity, but instantaneously you could have been going 75 miles an hour or 25 miles per hour. So that's the difference between the average and instantaneous. I'm going to give you a couple of minutes to jot these down. If you write slow, take a screenshot, take a picture with your phone, whatever you need to do, but we want to make sure that these end up in your notebook as something that you're familiar with. So take a couple minutes, I'll give you some silence and let you go from there. All right, take the next 30 seconds to finish up or take a screenshot, and then we're going to move on. So 30 more seconds. All right, 5, 4, 3.5, 3, 2.5, 2.25, 2, 1.5, 1, going, and stop share. All right, so that gets us through that. I got one last probe we're going to finish with, and then we're going to talk about the assignment. So let's bring this one up, and let me share this one with you. All right, what do we have? This is a go-kart test run. With any graph that you draw, make sure you give it a name and then label the axis. Ideally, you would have units as well. Here it has position minus the units. They're bad. Over time. So anytime we do time, it'll be on the x-axis. So that's time in seconds. So this tells us that Jim and Karen have built a go-kart, and they take their go-kart for a test run and graph its motion. So this is a motion. This is a position versus time graph. Their graph is shown above. They show their graph to their friends because these are really boring kids and they graph things and share with their friends. This is what their friends say. So we've got 4 different friends that analyze this graph, and we've got to figure out which one is correct. So I'm going to read through them. Like Bill will be 1, Patty 2, Carrie 3, Mort 4. And then once I get this read through, I'll look for a quick finger survey of who's right. So Bill says, wow, that's a steep hill. You must have been going very fast at the bottom. Where Patty says, I think you were going fast at first, but then you slowed down at the end. So Bill and Patty are kind of, I guess, opposites of each other. One says fast at the end, the other says slow at the end. Carrie says, I think you must have hit something along the way and come to a full stop. Where Mort, whatever kind of name Mort is, says, it looks like you're going downhill and then the road flattened out. So get your idea, 1, 2, 3, 4, stop the share. All right, let me see, 1, 2, 3, 4, who's right? I see a lot of people not voting, come on, fingers up. All right, I see 4s, lots of 4s. I see it, wait, I think somebody changed. All right, who went from 3 to 4? Come on now. All right, lots of 4s. Let's go back and you can put your fingers down. Let's go back to the screen share and take a quick look. All right, now it's a position versus time graph, right? And most people just kind of disagreed with what was going on down here because one said you're going fast, one said you're going slow, one said you stopped, and the other one said the road flattened out. All right, well, Mort said the road flattened out, but this is a position versus time graph, okay? So at time point 0, right, this is time point 0 right here, and I come up, I'm at position 10. Let's call these meters because it's not labeled. We can make it what we want. So I'm at 10 meters. I'm at the 10-meter mark at position at time point 0. And then at 2.5 seconds, because that's halfway to 5 seconds, at 2.5 seconds, I'm at position 5. So I'm moving, right? In 2.5 seconds, I went from 10 meters out to 5 meters out. So I'm coming in closer to position 0, the origin, and I'm moving. Now, what about right here at about 6 seconds? I'm at about position 1 meter. What about 7.5 seconds? I'm still at position 1. At 8, 9, and 10 seconds, I'm still at position 1. Can we see that this line is flat? And that means the position, what's graphed on the y-axis, isn't changing. Time is moving along, but the position is staying flat. So here, Carrie, the third person, was correct. Because when we first look at these graphs, we want to interpret that graph as being like an image of the hill that the cart went on, right? But what we need to do is we need to look at the axis and say, what is it actually? It's graphing not a picture of the hill, but it's graphing for us the position of the cart. And when that graph flattens out, that means the position's not changing, okay? So that's just something we want to be very aware of. So the next thing we're going to do is we're going to go into the walking lab, but I'm going to give you some notes on it first, or write some things and kind of give you some hints on how to do this. So let me go back to this other one and see if I can much more smoothly share this screen again. All right, so share application, grid. All right, so we're back to this picture we were at. I'm going to scoot this guy up a little bit because I think I have enough room to write here. And then I'm going to recreate a position versus time graph. So if I were to draw, yeah, you can see it. So if I've got a graph, and I'm going to call this a motion graph because I don't have a better name. So this is motion graph. Showing up, yep. On the y-axis, I'm going to call this my change in position, so my delta x, because x is position, okay? And it's going to be in meters. The y graph, I'm sorry, the x-axis is going to be time. And I'm going to measure that in seconds. That funky looking S5 thing, that's seconds. Okay. So if I was to, what you're going to do for this exercise is you're going to watch a video that we created. You would have actually participated and done this lab had you been able to be on campus today. But yesterday, we got 7 teachers together and we did a lab. Unfortunately, I'm not in the video because I was the one holding the camera, but Mr. Hennessy does 4 different walks, and you're going to take the data from the time points. So we marked it at 2, 4, 6, 8, and 10 meters, and then the time was in seconds. And then you're going to basically plot one walk, so kind of get that data. You're going to draw a best fit line. So let me see, I need to draw a shape, which is here, there. So then I'm going to take a best fit line, and I'm going to draw it through that data. Now, that is a best fit line. There's some things that you should know about a best fit line. Number 1, don't force it through the origin. Number 2, you're not connecting your first and last data point. And number 3, it should represent your data, but it does not necessarily have to go through any point. Now, Mr. Hennessy did start at the starting point for 3 out of 4 of his walks at time point 0. So this data does go through the origin. But don't force your best fit lines through the origin. Once you draw the best fit line, you don't care about the data points anymore. They don't exist. So you'll end up drawing lines for 3 of his walks. Let's just do them like that. So you'll have 3 walks, and then his 4th one, you'll find actually goes in reverse, goes across this way because he went the wrong direction. Once you draw the lines, the data points don't exist, only the lines do. From the lines, we can get the slope of the line. This goes back to geometry, but for anybody that forgot geometry because, well, it's been a long pandemic, we can say that, I'm gonna bring my notes over to make sure I don't forget to tell you anything in particular. We can say that the slope, I gotta switch to drawing it. The slope, remember how to calculate this with rise over run? So it's rise over run. Here, you are not using the original data points. You're finding new points along the line that the line actually hits, okay? Forget the original data points. Never, ever use them. Rise over run, rise is the change in X over the change in Y. So that triangle looking thing, that means change, delta change. So the change in X over the change in Y, remember the units of X is meters, and the units of Y is seconds. That's meters per second, which is velocity. So when we have a position time graph, the slope that we calculate is the velocity. It's how fast you're going. Now, every line has an equation. We probably remember most generically, let me put something down so I don't mess up. The most generic line equation, do we remember y equals mx plus b? Here, I'm gonna stop, or no, I can't stop sharing. Let's see, let me see if I can see more people. There we go. All right, remember y equals mx plus b? Okay, very, very generic. For us, y is our final position, okay? Position for us is x. I'm sorry, it's just the way it's gonna be. So y becomes x. It's not the x-axis. X just means position. If we look back over here at our graph, what did we label the y-axis? We labeled it x, right? So y is x. That equals, what is m is slope, right? Well, what did we say slope is equal to? Velocity?
Velocity.
Yeah, there we go. Hey, interaction. Love it. All right, so slope is velocity. All right, times, now what is our x-axis?
Seconds.
Right, but it's time, right?
Right.
Time in seconds? Yeah, but you're right, seconds, but we're gonna use time. And then plus, now B. B is the y-intercept. But when do we hit the y-intercept? Don't we hit it at time point 0? Right? When you cross the y-axis, aren't you doing it at x equals 0? All right, if that's true, which it is, that's going to be our initial, our starting position. We're going to call that x naught. Anything with that little circle underneath, that subscript circle, that just means initial. So our final position, x, is equal to how fast we're going times that amount of time plus our starting position. So if I move 10 miles an hour for 1 hour down I-20, I'll end up 10 miles from my starting position. So we can say my final position is equal to my velocity times time plus my starting position. Okay. If we do just a little bit of algebra, we can subtract the initial position from both sides. And what we would get is x minus x naught is equal to velocity times time. Well, final minus initial, that's just a change in velocity, change in position. Final minus initial would be delta x is equal to v times t. So now we've taken an equation, y equals mx plus b, our geometry equation, and we've turned it into our physics equation. Delta x is v times t. And that's just saying my displacement will be equal to my velocity times time. If that doesn't make sense, I can ask you in a different way. If you go for 5 miles an hour for 1 hour, how far will you go? You'd say, probably say 5 miles. What if you did it for 2 hours? 10 miles, 3, 15 miles. That's what this is saying. How far you go will be equal to how fast and for how long. Okay, really, really kind of hitting the surface on a lot of these things. This is the point where now I can turn it over to you guys. Let me stop sharing the screen. At this point, I want you to be able to go into Canvas, find today's information. There's a walking lab. You'll go into the walking lab, you'll have to watch a video. At the end of the video is the data set that you're going to use to then answer the questions. That is to be submitted back to me through Canvas by midnight tonight, and that satisfies your asynchronous work. Your homework that we talked about is also linked right below that. Start working on it. Next class, we'll open the class with questions about what you worked on and then go into new material. Most classes will be like that. I'll assign some work and then I'll say, okay, what questions do you have? If nobody worked on it, I got no questions to answer and I move forward. So it's up to you to try things and then let's have discussions about where you have the sticking points. I'm going to stay on the Zoom until the end of class. You're welcome to jump off, jump back in. Stay. If you stay, just mute yourself. And then whenever you have a question, just come out and mute, ask the question. We'll discuss it and I'll be here hanging out until the end of class. Anything for me right away? Start working on it. You have to have it done by the end of next week, but if you wait till the last minute, you'll show up on quiz day and say, hey, I have a bunch of questions. And I'll say, great, I got 3 minutes before we start the quiz.